Hello Kubernetes fans. In this video we'll be diving headfirst into the world of dual-stack Kubernetes clusters. We'll be setting one up on a shiny Ubuntu 24.04 LTS which just landed not too long ago. A dual-stack cluster lets you leverage both IPv4 and IPv6 for communication, giving you extra flexibility and future-proofing your Kubernetes deployment. Throughout the video, we'll be covering setting up our Ubuntu 24.04 environment, installing and configuring container runtime, initializing our Kubernetes cluster with a dual-stack networking setup using Flannel networking fabric. By the end of the video, we'll have a dual-stack Kubernetes cluster up and running on Ubuntu, ready to take on your containerized workloads. So, smash that like button, let me know in the comments if you're excited about dual-stack Kubernetes, and let's get started. We have three identical VMs, Node 1, Node 2, and Node 3. Each VM is running basic Ubuntu 24.04 long-term support server flavor. Mind that Ubuntu 24.04 is based on upstream kernel 6.8. As we'll be running a dual-stack configuration, our nodes have both a private IPv4 address and also a global IPv6 address. To make the network easier to manage, I've assigned a static IPs to each device. Node 1 has .10 IP, Node 2 has .11 IP, and Node 3 has .12 IP for both IPv4 and IPv6. Our Kubernetes deployment will consist of a single node running the control plane that manages the state of the cluster, and two worker nodes that will run our containerized workflows. Mind that if needed, you can add more worker nodes to the cluster. Also, for high availability, you can have multiple control plane nodes, but let's leave that for another video. A 1000-feet view of the Kubernetes architecture. As a part of the control plane, we have an API server. It acts as a single point of entry for all Kubernetes commands. It receives requests from users and applications, validates them, and sends them to the appropriate components for execution. This is a RESTful API. Another component of the control plane is the scheduler. It decides on which worker node a pod should run based on factors like resource availability and pod requirements. We also have a controller manager. It manages the lifecycle of various Kubernetes resources like deployments, replica sets, and pods. It ensures these resources stay in the desired state as specified by the user. Lastly, the configuration is stored in etcd. That's a highly available key value store. If we look at the worker node, there's the kubelet. It's the node agent that runs on each server in the Kubernetes cluster. It receives instructions from control plane about what pods to run. It then talks to container runtime to run those pods. So basically, kubelet manages container lifecycle on the node. It starts, stops, and monitors containers based on control plane directives. It also reports the node and pods health back to the control plane. Finally, we have pods that host our containerized application. A pod can contain one or more containers. There are also few other components like kubeproxy or core DNS, but they deserve their own video. We'll start with changing a few options necessary for Kubernetes to work. Following steps should be executed on all three nodes. For demonstration purposes, I will only show the process for node 1. First thing first. For pods to communicate across the nodes in the cluster, we need to enable IP packet forwarding for both IPv4 and IPv6. This option allows packets to be routed between different network interfaces. The thing is, when pods on different nodes need to talk to each other, the packets need to be routed between the nodes. Without IP packet forwarding enabled, the kernel on each node would treat packets destined for pod's IP outside of the local node as invalid and drop them. To enable packet forwarding, let me open the sysctl configuration file that stores kernel tunable parameters and uncomment this line. That's responsible for IPv4 packet forwarding, and this line that's responsible for IPv6 packet forwarding. Finally, Let's load the configuration with sysctl-p. Next thing we need to do is disable swap, as Kubernetes relies on predefined resources requests and limits for pods. Disabling swap ensures all allocated memory remains easily available for the pod. Basically, when a pod tries to exceed its memory limit, Kubernetes can gracefully evict the pod or throttle its resource usage. This ensures predictable behavior and prevents resource starvation for other pods. If swap was enabled, then when a pod uses more memory than allocated, it might start swapping data to disk. This becomes unpredictable for Kubernetes as it cannot guarantee the pod's actual memory usage at any given time. Moreover, swapping data between memory and disk is significantly slower than accessing data directly from RAM. To disable swap, I will open the file system table that defines mount points and comment out swap so it's not mounted during boot. To make the change immediate, I will disable the swap from the command line with swap off command. If we look at the amount of free memory, we'll discover that the total swap size is 0. Last thing we need to do is update our system with apt update and apt upgrade and make sure few core binaries are installed. We've prepared the operating system, and the next step is to install the essential components for running Kubernetes. This involves adding two repositories. First is the Kubernetes repository that will provide the core Kubernetes tools for managing and running your cluster. Second is the container runtime repository that will house the container runtime software responsible for executing containerized applications. To verify the authenticity and integrity of packages stored in the repository, we need to download the GPG public key from Kubernetes repository maintainer. Later, we'll use that key to validate if our packages have not been tampered with. I will use the curl command to download the GPG key, convert it to binary format with GPG command, and store it in the etc apt keyring folder. Next, let's add the Kubernetes repository to apt sources. I'm going for the latest stable version, that's 1.30. Mind that if we look at the file containing repository configuration, we'll see the signed by option. In other words, the key referenced by this option will be used to validate packages. Let's repeat the same step, that is, download the public GPG for Docker repository, followed by adding Docker repository to apt sources. Taking a peek at the repository configuration file, you will notice the architecture is set to AMD 64. This indicates the packages are precompiled for 64-bit Intel and AMD processor, a common architecture. By specifying this option, we'll ensure we download packages compatible with our system. Additionally, the file includes the codename of our Linux distribution. This information instructs apt, the package manager, to select the appropriate software version relevant to our specific system. Let's refresh our package list with apt update. That will download package information from all configure sources, including Kubernetes and Docker source that we've just defined. Now it's time to install the container runtime. That's the engine that allows you to run containerized applications. The most popular choices are Containerd and CRY-O. We'll go with Containerd as it's the default. In a different video, I will show you how to use CRY-O. Let's proceed with apt install. One thing that's crucial to understand, Kubernetes is a container orchestration platform. It automates tasks like deciding where to run a container, making sure it has necessary resources, adding, removing containers on demand, distributing traffic among containers, and so on. Container execution is handled by container runtime that's not part of Kubernetes. In fact, Kubernetes can use any runtime compatible with CRY, container runtime interface. CRY is like a protocol, a set of rules that allows Kubernetes to talk to container runtime. By decoupling container runtime from container orchestration, we have great flexibility. There's One parameter we need to tweak in containerd runtime configuration. Let's first dump containerd default configuration and save it to a config file. We'll use it as a starting point for custom configuration. Now, let's open the configuration file and change the systemd cgroup parameter to true. Now let's restart containerd service to reload the configuration. Why the cgroup driver matters for Kubernetes? The Linux kernel provides a powerful feature called control groups that abbreviates as cgroups for managing resources. Cgroups allows us to limit resources like CPU or memory, prioritize processes, isolate them from each other, and track their resource consumption. In Kubernetes cluster, two key components rely on cgroups. Kubelet, this process runs on each worker node and is responsible for managing container lifecycle, and containerd. This is the container runtime engine that executes container workloads. Both kubelet and containerd interact with cgroups through cgroups driver to manage resource allocation for containers within the cluster. On Ubuntu, the init system managing process at startup is systemd. Systemd also uses control groups for defining resource limits, tracking processes, and overall system management. By default, kubelet leverages the systemd cgroup driver. Setting the systemd cgroup driver parameter to true ensures that containerd also utilizes the systemd cgroup driver. This is crucial because it creates a consistent view of resources usage across the system, with both kubelet and containerd using the same cgroup driver. There's no ambiguity about which control group manages resources, leading to more predictable resource allocation for your Kubernetes workloads. Our system is pre-configured, container runtime is ready. It's time to deploy 3 Kubernetes tools that play a crucial role in managing our containerized applications. First one is kubelet. It acts like a foreman on each worker node, taking instructions from the control plane and overseeing the execution of containerized application through pods. One thing to note, kubelet does not run as a pod. It runs as an independent process. The second tool is kubeadm. That's the tool used to bootstrap the cluster. It's responsible for installing essential control plane components like the API server, scheduler, and controller manager. It also initializes the etc store and generates certificates used for secure communication. Last tool is kubectl. This is a command line interface for interacting with your Kubernetes cluster. By using kubectl, you can view cluster information, create, edit, and manage resources, scale deployments, and so on. Okay, let's run apt install. Before bootstrapping your Kubernetes cluster, there's an optional step that can significantly speed up the process. Pre-pooling the container images required for control plane components. As mentioned earlier, kubelet runs as an independent process. However, other control plane components like the API server, controller manager, and scheduler operate within pods, which themselves are built from container images. By pre-pooling those images using the kubeadm config images pool command, you can ensure they are available on our nodes before cluster creation begins. This eliminates the need to download them during the bootstrapping process, leading to a faster and more efficient setup. The kubeadm config images pool command specifically fetches the images for API server, controller manager, scheduler, kubeproxy, core DNS, path container, and etcd. Pre-pooling those images is an optional step, but it can be a valuable time saver, especially for environments where network bandwidth may be a concern. Finally, let's bootstrap the cluster with kubeadm init command. Kubeadm requires some configuration parameters. You can either pass those parameters to kubeadm via command line or provide a configuration file for more advanced options. Let's take that route. I will create a kubeadm configuration file. For kubeadm init, there are 4 types of configurations that are supported. init configuration, cluster configuration, kubelet configuration, and kubeproxy configuration. We'll modify the cluster configuration, which defines key settings for the entire Kubernetes cluster. First thing we need to set is the pod subnet. That's a range of private IP addresses reserved for assigning unique IPs to pods within the cluster. We'll set the IPv4 network range to be 10.254/16. That's over 65,000 addresses. As we want a dual stack setup, we also need to define IPv6 range. For IPv6, we'll use the FC00 addresses that fall under ULA, that stands for Unique Local Address. The FC00 range has a similar function to a private addresses in IPv4, so it's not routable over the internet. Let's set it to FC00:10:244/56. Remember that every pod in your cluster will be assigned a unique address from the pod subnet. Pods leverage these addresses to communicate with each other directly. Why/16 for IPv4 and why/56 for IPv6? I will explain that in a second. Let's also assign a service subnet. That's an IP address range that cluster IP services are assigned from. Cluster IP is the most common type of service in Kubernetes. It creates a virtual IP address that does not change. It's built in front of a group of pods, make it easier to access them. Feel free to watch my video on Kubernetes services to learn more on cluster IP. For IPv4, let's set 10.96/16. For IPv6, let's go with FC00:10:96/108. Mind that service subnet cannot overlap with pod subnet, and that service subnet is a range of private IP addresses. For demo purposes, I've set the IPv6 subnet to its maximum size, that's /108, 1 million addresses. Usually, /112, that's 65,000 addresses, is sufficient. Another resource type we need to create is initial configuration that holds the runtime configuration specific to the node where kubeadm is running. First, we'll set the local API endpoint. It defines the IP address and port for the API server instance that will be deployed on the node. By default, kubeadm tries to auto-detect the IP address of the node's default network interface and uses that for the API server advertised address. I recommend setting this option to ensure your API server is reachable on the intended network, especially if you have multiple network interfaces. Another important setting is node registration. It holds fields that relate to registering a new node to the cluster. We want to set the IPv4 and IPv6 address that the kubelet should use to advertise itself to the Kubernetes master. Finally, let's save the configuration. Let's run kubeadm init and pass the newly created configuration file. Here's what kubeadm init command does. First, pre-flight checks. It begins with a series of pre-flight checks to ensure your system meets the minimum requirements for running Kubernetes. This step validates your system readiness for a smooth initialization process. Then, certificate generation. Secure communication within the cluster is crucial. kubeadm init generates a set of certificates for various Kubernetes components to establish secure communication. Kubeconfig files. To connect to the API server, components like kubelet, controller manager, and scheduler require kubeconfig files. These files are created and stored in the etc Kubernetes directory, where admin config is for kubectl and other files are for other components mentioned above. Then we have pod manifests. The command creates pod manifest files, essentially blueprints that define the configuration for the API server, controller manager, scheduler, and etcd. These manifests are written to the etc Kubernetes manifest folder, which the kubelet continuously monitors. Then we have kubelet startup. Once configured, the kubelet service starts running on the initial node. Then we have pod deployments. The kubelet reads the pod manifests from the designated folder and proceeds to launch all the defined pods, bringing up the core Kubernetes control plane components. Then there's the configuration persistence step. For future reference and potential retrieval, kubeadm stores both the kubelet and kubeadm configuration as config maps within the cluster. Then there's the node preparation. To designate the initial node, that's node 1, as the master node, kubeadm assigns labels and tines. Tines essentially prevent the scheduling of regular workloads on this node, ensuring it remains dedicated to the control plane functions. Then we have the bootstrap token step, where secure tokens are generated. They are used for worker nodes during the bootstrap process. Finally, kubeadm init installs the essential pods for DNS, that's core DNS, and network proxy, that's kubeproxy. Once the control plane is up and running, let's switch to our unprivileged user and copy the configuration file that our kubectl command will use to connect to the cluster. First, I will create a .kube folder that will store our configuration. Copy the configuration file from etc Kubernetes to kubeconfig file. Let's also change the permission to the file so that our local user can access it. Mind that containerd and kubelet are running as processes, but other Kubernetes components like etcd, API server, controller manager, scheduler, core DNS, or kubeproxy run as pods. We see that core DNS pod is not working. Why is that? Moreover, if we look at the list of our nodes with kubectl get nodes, we also see that node 1, that's our control plane node, is not ready. That's because our container runtime network is not ready. In Kubernetes, the network layer is pluggable. You have a freedom to choose the network provider that best suits your needs. In other words, Kubernetes by default does not come with a networking layer to interconnect the pods. It expects you to provide a networking provider that implements the CNI, that's Container Network Interface specification. In future videos, we'll go via various networking providers in detail. To enable communication between pods across nodes in our Kubernetes cluster, we'll need a Container Network Interface compatible provider. Flannel is a popular choice and easy-to-use option for this purpose. Flannel works by creating an overlay network on top of your existing physical network infrastructure. This overlay network, by default VXLAN, allows pods on different nodes to communicate seamlessly as if they were directly connected to the same layer 2 network. We'll discuss Flannel in more detail in a dedicated video. Today we'll just scratch the surface. Okay, to get started, we need to download the Flannel manifest file. By default, Flannel only uses IPv4. To have a dual stack setup, let's open the Flannel manifest file. First, I will enable IPv6 support. Then, let's provide the IPv6 network for pods. It needs to match what we provided in kubeadm configuration file. The reason we are specifying /56 is that Flannel assigns /64 for every node for IPv6 and /24 for every node for IPv4. Let's save the configuration and deploy our Flannel CNI. Okay, Flannel did set up a daemon set that spawned the kubeflannel pod. Our pod networking should be operational. All looks good. Our core DNS pod started working. Let's enable scheduling of pods on our master node as it's disabled by default. To do that, we need to remove no schedule tint from the node. This approach is generally not recommended for production environments due to potential security implications. You should have a dedicated, highly available control plane with multiple master nodes for redundancy and fault tolerance. However, for single node deployment, there is no other way to run a control plane and worker on the same machine. Now that our Kubernetes control plane is up and running, we can proceed with adding worker nodes to expand the cluster capacity. Let's switch to worker node 2, where we'll create the necessary configuration file for it to join the cluster. This configuration will be of type join configuration, which specifies the details required for the worker node to join the existing cluster. A critical part of the join configuration is specifying the API server endpoint. This endpoints defines the location of the master node's API server, the central control point of Kubernetes cluster. To provide this information, we'll need the IP address and port of the master node, nodes 1 in this case, where the API server is running. Let's get the join token from node 1 and put it in the token field on node 2. Let's also grab the certificate hash and put it in the respective field in the configuration file. Finally, let's advertise our kubelet IPv4 and IPv6 address. Let me run the join command with the newly created config. Okay, node 2 joined the cluster. I will go to node 1 and list the nodes. Node 2 is there. Let's go to node 3 and create the kubeadm configuration file so it can join the cluster as well. I will copy the config from node 2 and update the IPv4 and IPv6 address. Let's run the join command. Okay, node 3 joined the cluster. Let me look at our nodes. All 3 nodes are operational. If I list the pod subnets, we can see that each node has a /24 IPv4 and /64 IPv6 network range allocated. Our basic 3-node Kubernetes bare metal cluster is up and running in dual stack mode. To validate if it's working, let's run an Alpine Linux pod. If we look at the pod's network address, we'll see IPv4 and IPv6 addresses assigned. Exactly what we wanted. Alright folks, that's it for installing a dual stack Kubernetes cluster on Ubuntu. This should give you a solid foundation for running your containerized applications. But wait, there's more. To take your cluster to the next level, you want to explore Metal LB for load balancing to distribute traffic across your pods for high availability, metrics servers and monitoring to gain insight into your cluster health with metrics collection and Grafana dashboards, and persistent storage to provide persistent storage for your stateful applications. We'll be covering all these topics and more on this channel, so be sure to subscribe for in-depth tutorials on Kubernetes. If you found this video helpful, don't forget to leave a thumbs up to let me know. Thanks for watching.